So let's just really quickly revisit the work we were looking at yesterday. So I had some videos for you, and those videos were, there was just one actually, sorry, but now there's a whole bunch. The video was of an air cart, and one of the things that we discovered yesterday was that, especially on Chromebooks, if you don't have it set to the highest quality, it jumps. How many of you noticed that? So I think some of the variation we were seeing may have been because your Chromebook was streaming at a lower resolution, so it was skipping frames. So the best way around that is to make sure that the quality is set to at least 720p. I haven't tried it at 1080, but that's the resolution, but I think the frame rate changes as well. And if you do that, then what you should see is that as you click through the video with the greater than and less than keys, it moves at a consistent rate. So if you're clicking and it seems to be like sometimes it doesn't move at all and other times it jumps, it seems to go like twice as far as it did the previous click, that's not right. And we'll talk about this in just a second, but for reasons that you already have a good foundational understanding of, these carts should be moving at very nearly a constant speed. Each frame is a 30th of a second. If you're moving at a constant speed, and each frame is a 30th of a second, then we should see the cart move the same distance every time, right? So what I asked you to do in class yesterday was find velocities. Find the velocity before and after the collision for each of these two carts. And we're gonna come back to that because what some of you probably realized is, geez, it's kind of a mess. It's really not that easy to keep track of these things. It's easy to find the velocities, but it's easy to keep track of which velocity is which. So I'm gonna show you my little system for doing that. I have a bunch of little systems actually for doing that, and there's a variety of ways that you can pull this off. The assignment itself has been posted. So yesterday I just said find the velocities. Today there's more detail. And so this is where we're going to get into a couple of skills, one of which is relatively easy, one of which is really challenging. So I mentioned already there's an algebra piece. I'm going to take care of that for you. That's not on the skills. But those of you in AP Physics just know what I'm about to show you algebraically, you've got to be able to do. The second skill, and these are in no particular order, so I'll talk about this one first. How well can you calculate momentum for an object, for multiple objects, and for a system of objects? And what that is about is that if you have two objects and they collide with each other, then you have 4 velocities potentially and 4 different momenta, right? That's the plural of momentum. And so you have to keep track of a velocity for one object, a velocity for a second object, and then a velocity for the first object later, and a velocity for the second object later. In our systems in general, the mass of each object is going to stay constant. In real systems, that's not necessarily true. We'll solve problems where the mass of things doesn't stay constant. It's absolutely possible for things to break apart and stick together in different ways. It happens all the time. So even the mass could potentially change. So we've got this record-keeping nightmare, and that's going to be the big push of what I show you this morning. And then your work is largely going to be around this, evaluating empirical data. So the carts that I used, I measured their masses. I had really good measurements on their masses. Are they perfect? No, but they're really close. The track itself is very well calibrated. Those markings are about 1 centimeter and they're very well spaced. Like, we can take distance measurements to the bank. Our times are very, very well calibrated. Those frames are as close to 1/30th of a second as anything. Like, we're not going to get closer to 1/30th of a second using any tools or equipment do we have? Like a digital video at 30 frames per second is stunningly accurately or precisely 30 frames per second. But beyond that, there's all sorts of room for error. So you're gonna count things wrong, or you're gonna have the cart in between two of the lines, or you are going to look at one point of the video and somebody else is gonna look at another point of the video, and things may appear different. And here's what's really interesting, is that even though we're all gonna be watching the same video, and there's actually 6 videos, there's 3 videos, and I put them on YouTube. I also uploaded 3 high-res versions of those for people who want to use Tracker. So there's a couple different ways that you can look at this data. With 6 videos of the same carts, 3 different collisions, we're gonna end up with like a huge variety of estimates for velocities and our other calculations that we're gonna make. And the big thing that I want you to start trying to really work on is, how can you know if you're right? Like, we're gonna get a bunch of numbers, and you're gonna get some numbers, and you're gonna get some numbers, and you're gonna get some numbers. I know what the real mass of each cart is, but I don't know what the real velocity is any more than you do. So there's all sorts of like ways that we can work together as a team to come up with numbers. And the way that I'm gonna propose thinking about this in general is, what if there were money on this? Like, what if, and this is actually how it works in real life. I can't pay you, obviously, but in real life, in engineering firms, and like people will have like informal competitions sometimes. There'll be a $10,000 prize for whoever can figure out blah, 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 blah. More commonly, there are engineering firms that are competing with each other to figure out the same thing. I watched an awesome video about the discovery of and creation of blue LEDs, which was a transformative technology. And it was really difficult. The smartest people in the entire world were working on this all over the planet, and one guy figured it out in Japan. And that company, the company that was able to capitalize on his discovery, made a fortune. So there's money riding on this outside of the classroom. If we were to pretend that I posed that we had a problem that we really wanted to solve, we really needed to know the answer to this, and somebody was gonna pay us $1 million if we could do this. Shoot, I'd split $1 million with you all 30 ways, that would be terrific. But we have to be right. So how do we ensure that we're right? That is the mindset that I want to have, is we want to be sure that we're right. How are we sure that we're right? Here are the kinds of things that we do. Number 1, take multiple measurements. Multiple measurements of the same video. Multiple measurements of different videos. We take measurements in a variety of ways. I posted videos on there, and the technique that I showed you yesterday allows you to do calculations using YouTube. You can step through the video, and you can use the marks on the track, and you can find velocities, but you have another way of doing it, which is Tracker. So I've posted MP4 videos that can be uploaded into Tracker. You can use Tracker to find the velocity of each of these carts before and after the collision. Maybe that's better, I don't know, because we haven't tried it yet. You can check each other's work, not just within a group, but that is a great way to do it. If you are working in a group of 2 or 3 people to do this, instead of the 3 of you working together, you could try tackling the problem separately and then coming together with your answers. That's what I would do if I wanted to be right. Because if 2 people kind of work collaboratively on a problem, they're more likely to come up with a solution. It's also more likely to be incorrect for some silly reason. If 2 people work separately on a problem and they each get the same solution, they're more likely to be right. 2 people independently arriving at the same answer is evidence of correctness, and that's what we want. So ultimately what we really want is consensus. We want to be able to say, here's what we think the answer is. And we want to have the same kind of confidence that we would want to have if there really were money riding on this. And then there's a bunch of information here, and basically what this boils down to is you should know this. Look at it, because it'll help you. But essentially what we're saying is we can find velocity here because it's constant, because the net force on the carts, each cart before and after the collision should be 0. And we have kinematic equations that, in the case of 0 acceleration, make it really easy to find velocity if we know how far something goes and how long it's taken, right? And then what you're trying to do is find the velocities of each of these carts before and after the collision. That's 4 velocities. I'll show you the record-keeping piece in just a second. And then, I try so hard, I really do. I meant to put the mass of the first cart in here. I'm gonna give you a mass. You're gonna have the mass of one of the carts, it's like 0.225 kilograms or something, but I'll put it in here so it'll be in here by the time you guys get to this. You're gonna use that to estimate the mass of the other cart. So let me show you 2 things. The first is, here's the algebra we're gonna use. This equation is one that was in the presentation yesterday, and I told you you needed to write down one part of it, but not the other part of it. Now I want you to write down both parts, okay? Here's the first part. It looks like this. This is the law of conservation of momentum. And just like conservation of money, if there's no momentum added to or taken away from a system, then this will be true. With money, we get money added to or taken away from the system when someone else is involved. So if we're looking at, like, if Lauren and I have, between the two of us, 30 bucks, that amount of money is gonna stay constant unless somebody else brings money in or we give some of our money to somebody else. With momentum, it's the same way. Momentum can get added to or taken away from a system. And the way that that happens is by having overall forces in the dimension of motion. So this will be true if there is no net force in the direction of motion that we're addressing. If we're looking at one-dimensional motion, like air carts on a track, then as long as there is no overall force on either of those carts in the direction of their motion, momentum will be conserved. There is an overall force on the carts in this case. It's friction, but it's real small. It's not a significant force. These carts are mostly, over relatively small periods of time, moving at a constant velocity. Okay? And if we start adding a net force to things, then momentum is no longer conserved. So when I tilted the track here the other day and rolled these carts toward each other, they were experiencing an overall net force in this direction. Momentum was not conserved in that case with if our system is just the 2 carts. Yeah?
So what you're saying is that in this scenario that you've created, the friction is small enough to where you can still use that and it would still be close enough to act.
Yes. Not only is friction small enough, but the amount of time that we need to look at is pretty short. Over a long period of time, friction will slow things down. Like if I roll this cart, like it slows down, it didn't even reach the end of the track, right? But if we looked at just like a third of a second, then it would be different. And a third of a second is 10 clicks on our YouTube video. So a third of a second is like that long. Over that period of time, it's gonna hardly slow down at all. It takes several seconds for it to slow down. So we've got small force, small amount of time. Those 2 things together can let us make this assumption. that there's really no overall force acting on either of our objects, okay? So this is what the equation looks like. You need to know this. If we have two objects and their masses stay the same and they collide, then we have an extension of this, because the momentum before the collision, some earlier time, is going to be the mass of one object times its velocity plus the mass of the second object times its velocity. That is our sum of momentum at one time. And then at some later time, if the masses stay the same, which they do in the case of the air carts and they will in the case of the super carts or the aluminum carts, then our masses stay the same, but our first object has a different velocity after it's bonked into, there's been a collision, it's bonked into the second cart. So the convention is, we call that V1 prime. Prime just means later. So we've got a subscript indicating which object, a superscript indicating the time. And the second object is going to have a momentum of m2 times its later velocity, v2 prime. So that is our sum of momentums of our system later. This is true when we have two objects interacting and there's no net force in the direction of motion of either of those objects. This would be true three-dimensionally and two-dimensionally. When we're looking at it one-dimensionally, things get relatively straightforward, because each of them can only move in one direction or another, which means these velocities are going to be positive or negative, and we don't need to play any vector games with them. The masses stay the same, which means if we can measure essentially we have 6 variables here, right? 1, 2, 3, 4, 5, 6. We can measure 5 of those. We can find the 6th. And we can do that with any of these. So we can solve this equation for any one of our 6 variables. In the case of the activity that we're doing now, what I'm asking you to find is M2. Here's where the algebra comes in. And again, if you're in AP Physics, you better be able to do this. If you're not in AP Physics, then you don't need to be able to do this. So to get our M2s on one side, I'm going to subtract M2 V2 prime. I'm going to subtract M1 V1, and I get M2 V2 minus M2 V2 prime equals M1 V1 prime minus M1 V1. And then I factor out M2, divide by V2 minus V2 prime, and I get that my second mass should be equal to M1 V1 prime minus M1 V1, all divided by V2 minus V2 prime. This is an equation that you can all use now. If you know the mass of one object and the velocity before and after the collision for each object, you can find the mass of the second object. V1, V1 prime, V2, V2 prime, you're going to get from the videos. M1, I'm going to tell you, and I'm going to put it on the assignment because that's where it should have been to begin with. How do you keep track of all this stuff though? This is going to look a little silly to some of you, but this is how I actually keep track of it. I have to do it this way. If you ever come to me with a one-dimensional conservation of momentum problem, you will see me make the following diagram. I've been doing it for 30 years and I have no way of changing it now. I'm too old and inflexible. You might have a better way of doing it, but if you do it this way, I'll be able to follow what you've got. If you don't do it this way, I can't guarantee it. Those of you who work with Ms. Adams in any capacity, you're going to be asked to do it this way. You're going to have to do it this way. So whether or not you like it, please know how to do it, because this is the way that you're going to communicate to us what's going on. So this is a universal setup for two-dimensional collisions between two objects. And you'll see, not now, but down the road, that we can modify this to deal with a couple of kind of interesting situations where we have like one object that breaks into two. or we have two objects that combine into one. We can still deal with it using this framework. And the way it works is you draw the objects as boxes. You label the objects with their mass. You're gonna have two sides to this diagram. The left-hand side is before the collision. I use a lightning bolt to indicate the collision because nothing's more exciting than that. After the collision, we're gonna have the same two masses. On the diagram, draw arrows to indicate the initial velocities of each object. Could be different. In the case of the air car collisions that you are looking at today, they all look the same. The first cart is going this way, the second cart is going this way. After the collision, they bonk into each other. They both, always in all three collisions, go in opposite directions. That's not universal. That's true for this case. Underneath each object, you record its mass, its velocity, and its momentum. Some of these things you're not going to know, and I'm using the same terminology here. P1 prime is the momentum of this first object after the collision. Some of these things you won't be able to find. You don't know the mass of object 2. You won't be able to find the momentum of object 2. You just simply won't be able to do it. Down the road, we're going to use this system to organize the algebra so that we can find any unknown. For today, this is what's key. Keeping track of this and keeping track of it in this way is really key. Because then whatever unknowns we have, you'll be able to find. I have a solver for you for this. We're not going to use it today because we don't need it. But down the road, you'll be able to put some of this information into a solver. In this case, we know what direction these things are moving both before and after the collision. In this particular activity, we know that, which means you know mass 1 before the collision should have a positive velocity, mass 2 should have a negative velocity. After the collision, it's the opposite. Mass 1 should have a negative and mass 2 should have a positive velocity. This is all assuming that our positive direction is to the right. That means P1 should be positive, P2 should be negative, P1 prime should be negative, and P2 prime should be positive. When you make the diagram this way, you see the directions, helps you keep track of the signs. You see the before and after. That helps you keep track of the primes. And then, when you start working with the equation, it's much easier because you don't have to try to, in this case, this is what we're going to be looking at, you don't have to try to remember which of the velocities you wrote down on some sheet of scratch paper is this one and which is this one, right? Like if you just say v equals 2.1 meters per second, when you look at that later, what you're going to see is one of these four things is 2.1. Well, I don't know which one. And if you're like me, then as you do this work, you're often going to forget the negative signs. I did that yesterday while I was working through this problem. And so what ended up happening was I got the wrong answer. I figured out my mistake because I knew what was going on, but if you use this system, you'll spot that because you'll know, well, this one's going to the left. That means this should be negative and this should be negative. This one's going to the right. That means this and this should both be positive. As you write that information in on this diagram, you'll notice, oh crud, I put, this is positive, but I put a negative momentum here. That's not right, and then you can address that. So this is how you're going to find the second math in terms of the algebra and in terms of the calculations and measurements. So this is the record keeping piece. That's one of the skills that I want you to be working on. Another big skill that I want you to be working on is just trying to interpret this data. plug in numbers all day long and get a bunch of different values, but there is a right value, and I know what it is. We won't always, but we'd like to converge on that right value. Some of you are gonna do the YouTube like calculation stuff quickly, and that's great. And then if that's you, I really want you to try to use Tracker with this, because this is where Tracker becomes useful. We're not always gonna have, like, we're not always gonna know the frame rate of a video if we don't know that it's, 30th of a second per click, and everything else is off. We might have things moving two-dimensionally. It becomes a lot more difficult to figure all this stuff out if things are moving two-dimensionally. In this case, the ruler that we're using to measure distances is aligned with the object's motion. That's not always true. We could use Tracker to look at the momentum of two projectiles that collide in midair. We couldn't do that with the clicking method. It would be too hard to figure out how far things went and in what direction. So using Tracker ultimately might be really helpful for this. All right, so this is your task, and one final plea that I feel like everybody here is getting this. I feel like we are largely locked in, but I just want to make sure that you understand. In my universe, this is a fun problem to solve. Yesterday, I did this because I wanted to. I got Tracker and I had fun doing it. And I know that's not going to be the case for all of you, but I would love for it to be the case. What would be great is if you thought to yourself, okay, cool, mystery. What's the mass of that second card? It's not the same as the first card because there's something on it. And let's see how close I can get. That's how I approached it, and it was fun, so I know it's at least possible. Okay. All right, if you have questions, let me know. And you all can get to work. We've got maybe some other stuff to do as we get toward the end of the period, but maybe not, and I don't know how we'll deal with that later. But